Thank you very much for the too flattering introduction, but I'm really very happy to be here and for the invitation to be at this wonderful graph drawing conference. So the talk today is called A Sketch of Parameterized Complexity. You will see the word tree width coming up at certain places, but the focus will be on the topic of parameterized complexity. What I want to do is showcase a few of these notions of the field. And basically the talk has two parts. For some of you, the first part may be already things you might know, because I want to give a survey of the most important things with examples. When I could, I took examples from graph drawing to illustrate things. So the focus is more on complexity than on algorithms, although you will see some algorithms. And in the second part, I will tell what is my current hobby, which I think is a useful development here and might be also nice to see. But let's start with why do people actually look at parameterized complexity? And my favorite story is the following. Suppose you are the mayor of a city and you have to put fire stations in your city, and everybody has to live 15 minutes drive away from the fire station. Now this is, you think, oh my, how am I going to solve this? This is an NP-complete problem, right? It's impossible. But then the financial man of your city comes to you, say, we have money for 3 fire stations. And suddenly this problem becomes much easier, because you could just try all n to the 3 different possibilities. You have a polynomial time algorithm to solve this. So this is what happens in parameterized complexity. We have a problem. It is probably hard, but there is some parameter, some parameter of your input, of the answer which you want to have, which you think is small, and then that makes the problem easier. So in the 1990s, Downies and Fellows, they basically built on this theory and on this idea, whole theory, and the whole field of parameterized complexity started. So the whole question is, I have a problem, a computational problem. There is a parameter, and now I want to know if this parameter is small, how is the time complexity then of that problem? And this field got new theory. They have their own lines of conferences. There are, I think, probably thousands of papers written in this field. So that's basically where I start and want to explain something. So what is a parameterized problem? It's actually where a normal problem is a set of strings. A parameterized problem is a set of where every element is a pair consisting of a string and an integer. And the string is what you would call the input, and the integer is what you would call the parameter, which you think is small. And then the time complexity is now a function of these 2 parameters, of the input size and of the parameter, while classic complexity looks as the function of, as the time as a function of the input size. So parameters can come from different things, and I'll give a few examples here. It could be the target value, something about your input size, or some structural parameter of your input. So you have seen already 1 planarity and k planarity during this conference a number of times, and if you look this as a computational problem, you can say, okay, I have a graph, integer k. This parameter is k, probably the number of crossings per edge is small, and then you want to know, can I draw this in the plane such that no edge has more than k crossings? It's a typical example of a computational problem where you expect that the parameter is small. And so there are more another type of parameterization is that you really say about the input itself. As you could have some complicated problem on graph drawing, where, for instance, for every edge you have an interval and you want to draw this graph such that every edge has a length which is in this interval. This problem might already be complicated even if the number of vertices is small. And then you could take really the number of vertices itself as a parameter. because the complication can come from these values of these intervals. But many of these problems, and we have seen that already also in this conference, is that you look at a structural parameter of your input. And the typical example is that you would look at the tree width of you want to have some graph drawing problem, like rectilinear planarity testing is that I want to draw my graph such that every edge is either a straight line horizontal or a straight line vertical line segment, NP complete in general, but then people have studied what happens if the tree width of this graph is small. So the tree width can be there, but it can be also something else, like for instance, for upwards planarity testing, people showed that this problem is actually easier if the number of vertices which have in degree 0, so is actually a small value, then it becomes fixed parameter tractable. So you can now have all, and you can look at the dimension of the graph, you can have lots of structural input values of your input, and then you can ask if this is my small variable, what happens then with the complexity? And also you can get even richer and landscape by looking at combinations of parameters. You can say, okay, for instance, not the target value is small and some structural value is small. And we saw this in the first talk, this conference, that where the proof was given that one planarity is NP complete for graphs of path width 4. So now we have or even the sum of two parameters, namely the number of crossings per edge, plus the path width would be my combined parameter here. So, as I said, the question is really, what is the time complexity as a function of both these parameter, both input size and parameter? So the most well understood cases are the classic ones, where you could say, okay, the problem is polynomial. There is a polynomial time algorithm solving it in a polynomial of the sum of the input size and the parameter. The bad classic case is what people call para-NP complete. That is that the problem is still NP complete even for some fixed value of your parameter. And so for instance, this result we mentioned from Prima et al., which we saw at the first lecture, this conference, that one planarity testing is NP complete for graphs of path width 4. This means that K planarity is para-NP complete for this combined parameter. So that is what we call para-NP complete, and we are very unhappy if that is the case, because your small parameters actually don't help. So, but then something nice happens, that is when actually if your parameter is small, you have, say, fixed, something fixed, that you, for every fixed value of your parameter, you have a polynomial time algorithm. And two main flavors you have here. One is what we call FPT, fixed parameter tractable. That is that there is an algorithm and the running time is a function of your parameter times a polynomial, and this polynomial does not change. So you have, for every k there is an n square algorithm, or for every k there is an n to the 10 algorithm, but so the polynomial stays the same even if the parameter would grow a little bit. And then you have XP, which is an acronym for slice-wise polynomial time, where you have also for every fixed k there's a polynomial time algorithm, but now the polynomial grows when your parameter is growing. So you have an n to the function of your parameter time. So these are the two flavors. And as I talked about different parameterizations, if you can have the same problem and you can use different parameters, and with different parameters, the complexity may change. And so for one parameter, the problem may stay NP complete. For another parameter, it might become in XP, and for yet another parameter, the problem might become fixed parameter tractable. And this is actually a diagram from the proceedings of graph drawing last year, where the authors, Depian et al., showed for different parameterizations that you really have this different type of behavior. So one of the running examples was upward planarity. So here is just the problem again. It is, I want to draw a graph. I have given a directed acyclic graph, and I want to draw it such that all the arcs are having an increased value in the y direction. And this was already known for about almost a quarter of a century, that this is NP-complete in general. And here again you have this, you can see that there are these different types of parameterizations. If you parameterize it by some structural parameter called tree depth, is FPT, by the number of sources as well. I'll sketch something about that there is no polynomial kernel for parameterized by tree depth. But if you parameterize by XP, it's actually by tree width, its problem becomes in XP, and there is evidence that it's actually cannot be in FPT, and I'll discuss that later. So FPT is, as I said, a class of parameterized problems with an algorithm that runs in time a function of your parameter times a polynomial, and in the classic definition, you want that this function is computable. There are different variants. Weakly uniform actually means that you don't need that this function f is necessarily computable. Well, this is in theory a different class with difficult diagonalization arguments. Downey and Fellow showed that it's actually different, but there is no known example of a problem that people actually looked at in practice, which is weakly uniform and not normal, not strongly uniform. But you have another class is non-uniform FPT, and that is that you have for every k, you can have a separate algorithm. So, and that actually happens in practice. You can have that in practice. This, for instance, if you have graph minor theory, there is a non-constructive proof that there is a finite characterization of your problem for every fixed k. You have a non-constructive proof of a finite characterization, and there is an algorithm that, given this finite characterization, actually checks that whether it holds. So you have for every k, you have an algorithm, but we don't have an algorithm for every k. So FPT has a relation with kernelization, which I'll discuss next. And there is a reason to you use the W hierarchy, which I'll introduce later, that shows that problems are probably not in FPT. And you can actually show non-conditional that FPT is really a subset, a real subset of FPT using a diagonalization argument. So there are XP complete problems which are not in which we know are not in FPT. So what is kernelization? The next thing I want to discuss. Well, in practice, if you have a difficult problem, you might first preprocess it. For instance, I have a graph problem that I know that vertices of degree 1 and 0, well, they don't do anything. So you could just remove these vertices of degree 1 and 0 and then take the remaining graph and solve that on that graph. So I have a smaller graph with the same answer. Now, kernelization is this idea, but then with the additional requirement that the results you get after this preprocessing phase is actually provably small. And provably small means that I want an equivalent input whose size is a function of my parameter only. So here is the formal definition. A kernel or a kernelization algorithm is an algorithm that takes an input of a problem, maps it to another or maybe the same input of the same problem. This algorithm uses a polynomial time, and I want that both the new parameter and the input size of the new input are bounded by some function. So I get a new input and everything is bounded by a function of my parameter. And of course then the last thing is that the answer stays the same. And this is what we call a kernel. And there is this nice relation with with FPT, namely if a problem is decidable, then it actually has a kernel if and only if it's fixed parameter tractable. One direction is simple. If you have a kernelization algorithm, what you can do is first you run the algorithm, polynomial time, then you have an equivalent input whose size is bounded by a function of a parameter. Problem is decidable, so you decide on this. And the running time is a polynomial of your original problem plus a function of your parameter. So that's FPT. The other side is a strange proof, and when I heard it the first time, I felt a little bit it's like cheating, because suppose I have a problem which is an FPT. So I have an algorithm running in some function of k times n to the c time. Now I take that algorithm, I run that n to the c plus 1 steps. Two things can happen. It can terminate or it cannot terminate. If it terminates, then I know the answer. So I have my kernel, or very formally, you would give a trivial order 1 size yes or an order 1 size no input, but you're done. If it doesn't terminate, then I know that n to the c plus 1 is smaller than f k n to the c. I mean, I have, so because the algorithm didn't terminate. So divide left and right by n to the c, I know that n is smaller than f of k. So I can actually really take the input itself, and the input itself is bounded by a function of your parameter. So I have a kernel, a very boring kernel, but it is one. What this, of course, also shows is that if you know that the problem is not FPT, then you also know that the problem does not have a kernel. So that is actually, the theorem is actually useful also for that purpose. So this part of kernelization, I want to finish with really a computational example of actually a problem with a kernel. And a really nice and classic one is the point line cover problem. So I'm giving endpoints in two-dimensional space, and I want to have k straight lines that cover all the points. So here's an example of a set of points, 3 lines. So this is a positive example if k equals 3. So this problem has, and k, the number of lines, is my parameter here. So this has a kernelization algorithm, and the first step is the following. If I have a line which covers more than k points I did not yet cover, I choose that line. I mean, if I don't take this line, I have to have every point has to have a different line. So I have to take this line, otherwise I need k plus 1 lines. So I take this line and I cover all these points, or maybe you just remove. One of the things you can do is remove these points and decrease k by 1. And you have an equivalent input with fewer points. So I repeat this step while possible. So at some point this step is no longer possible. Now after this step is no longer possible, each line covers at most k points. And I'm allowed to use k lines, so I can with these k lines I can cover at most k square points. So if n is larger than, if the number of points is larger than k square, I say no. And otherwise, I have an input with the number of points at most k square, so I have my kernel with k square points. So this shows that point line cover is fixed parameter tractable, and I have this kernel with k square points. This we call also a kernel like this a polynomial kernel, because the size of my kernel is actually a polynomial in my parameter. K square, k to the third, all of these is called a polynomial kernel. And for if you design kernelization algorithms, the goal is to try to get an algorithm where the size of this kernel is as small as possible, but you really prefer something at least polynomial. So there is actually theory being made to show that problems likely don't have polynomial kernels. Likely in the sense that we build this upon a complexity theoretic hypothesis. There are some technical details which I show under the carpet, but the basic idea is that there is something which we call compositional, and if a parameterized problem is compositional and it is NP hard to decide the problem with the parameter given in unary, then this problem does not have a kernel of polynomial size unless something in the complexity theory happens that people there don't believe, which is co-NP is a subset of NP/poly, and that would also mean that the polynomial hierarchy would collapse to the second level, and people believe that the polynomial hierarchy doesn't collapse. So what is compositional? The basic idea is that I say that the problem is compositional if I have n instances, always the same parameter, and I can build one new instance with the property that this new instance is true, is a positive, if and only if at least one of the instances is positive. Well, in this case, if there's at least one of these instances, we call this or compositional, but you can also take the flavor that you say, I want this new instance is true if and only if all the instances are true. So one example how you can apply this is for upwards planarity with a parameter tree depth. And I'll just sketch the idea, but the first thing is we need to know two things, namely NP completeness. Well, a planarity is NP complete, and the tree depth of a graph is at most the number of vertices, so that you can give that in unary. So this is basically the first box checked, and the second is that it's end compositional. And for end compositional, we can do this in a very simple way. We take the disjoint union of the graph. So we have n inputs. So this is actually all we need to show. We have n. If we have n inputs of upward planarity, then this graph can be drawn in an upward. The disjoint union of these graphs can be drawn in an upwards planar way, if and only if each of the separate inputs can be drawn. So this shows that the problem is end compositional. The only thing you need to look at is what happens to the parameter. Well, if the tree depth of a graph increases by at most 1 if you take disjoint union of graphs of a certain tree depth. So this is the proof. So it's a very almost trivial proof, so you have also proofs that problems don't have, with much more complicated proofs. Although for half of all the questions you might ask, disjoint union is actually the way to answer, to get a composition. Okay, so this was the FPT part. The problem. So now I discussed XP, and so that's the problems which have an algorithm whose time is n to a function of k. Again, I want here that this function is computable, and many problems also have been known to be in XP, often by using something like dynamic programming or branching, but also some cases you can already show that the problem is in XP by just trying all possible solutions. For instance, if you have some question, are there k vertices such that some property holds, you can just try Ln to the k different sets, and if the property can be tested quickly, then you're done. There are very few XP-complete problems which are typically formed. There is some game on a graph where the parameter is the number of pieces in the game. And then people have shown that these are XP-complete, but most problems are not known to be XP-complete, but complete for some other class within XP. And the most well-known and most used for that are the classes in the W hierarchy. And so like if you want to distinguish P and NP, you use NP completeness theory, and you have a class, you have reductions, and this is a way to show for problems that are not likely to have a polynomial time algorithm. Here you have the same situation, although the landscape is much more diverse than the landscape because basically in real life, almost all interesting problems are polynomial or NP-complete. Here it's much more, you have W1 and W2 and all these things there. So I'll try to sketch what these W classes actually are. So originally they are defined with help of circuits, but there is a much simpler to understand definition in where you use logic. And if you're hard for W1, it's unlikely that you are fixed parameter tractable, because if W1 actually would be equal to FPT, then the exponential time hypothesis is false. So this means that if you have a W1 hard problem, it's really unlikely to have an FPT algorithm for it. So hardness you do with help of reductions. And then you have, for parameterized algorithms, you have to tell what is a parameter, what's the role of the parameter in the reductions. So we have a parameterized reduction. We have the same thing as usual, that you take an input of one problem, map it to an input of another problem, with the property that the inputs are equivalent. Yes goes to yes, no goes to no. Then the other conditions are that what I want is that the new parameter should be bounded by a function of the old parameter. This is important. And so you cannot do something like, if you want to go from vertex cover to independent set, the value k goes to n minus k. That you cannot do. But for you, so this is basically the second condition. Your parameter is also bounded, and this means that some of the existing reductions in literature for NP completeness proofs cannot be used here because they violate this thing. But on the other hand, I have a little bit more power because my algorithm, my reduction algorithm, actually can use FPT time. So it can use something polynomial into size, but I'm allowed to use exponential time in my parameter. This gives me a little bit more freedom to build things. And some of the classes in this whole theory have actually more restrictions, but I won't tell those details. And again, if you have a parameterized reduction from problem A to B, then if B is in FPT, then A is not in FPT. So you know that it's unlikely that B is not in FPT and A is not in FPT. So everything you prove W1 hard or do something, gives evidence. It's similar like in NP completeness theory. So now let's just walk a little bit through the zoo of the W hierarchy. And the first one, which you have seen already, I think, almost a dozen times this conference, is the class W1. Classic definition uses circuits and notions like depth and width, but the easiest way to define W1 is saying that are the problems with a parameterized reduction to a question which is called weighted three-satisfiability. Now the weighted is a little bit, it's not what you usually expect for weighted, but this is the way it's defined. So you are given a Boolean formula in conjunctive normal form with 3 literals per clause. So that's basically an input like you see in the 3-set problem. And I have an integer k, and now the question is, can I make this formula true by setting precisely k of the variables to true and all the others to false? So I want to have a solution of weight k. And this problem is, can be used, is basically as the generic problem of W1. And it actually, you can change the 3 by any other integer, at least 2, and you can change the exactly to by at most or at least, and you have, again, equivalent inputs. The most well-known examples of complete problems are independent set and clique. And there are many other known problems there. So we have, for instance, 2 years ago, a paper at graph drawing showed that upward planarity testing with 3 widths per meter and orthogonal parameter testing with 3 widths per meter are W1 hard. So then you have more classes. So you have W2. W2 is basically almost the same thing, but now my classes can be arbitrarily large. So I can have more literals than 3 in a class. So I have a Boolean formula in conjunctive form, like an input of sat, and then I want to know, can I make this formula true by setting exactly k variables to true? And the classic example of a problem here is dominating set. And then you have, after that, in this W hierarchy, there are more classes, 3, 4, 5, and so on. And basically what does WT say is, I have a problem which is, you can formulate in Boolean as a Boolean formula where this is a conjunction of a disjunction of a conjunction of a disjunction of a conjunction of, and then in the end you have literals. So an and of or a. So this is basically generalizing SAT, but then you have an ors and ands nested. But the nesting level is basically T. That's the idea. And then you can, well, the question is, can I satisfy this formula by making exactly k variables to true? There are, I think, very few, I think a handful of problems known to be complete for W3. I think that in the literature there are 1 or 2 problems known to be W4, and the rest is based, I mean, all the others are really formulated like a sentence of this form, but there are no natural examples after a while. And then you have WSAT, which is, I now have just a Boolean formula without any restrictions. Again, make it true by setting exactly k variables to true. And then the last one in the W hierarchy is WP. And here I don't have a formula anymore, but I have a Boolean circuit. And I want to know, can I output true by setting at precisely k of the input gates to true. And this is the way you can then define WP. So W1 as I said, W1 hardness tells that it's unlikely that the problem is FBT. And what does it mean that the problem is hard for W2? Actually, not really much more. It's even more unlikely because it's a larger class. All these problems in this W hierarchy, if you're basically are always, if the problem is complete, they're always of this form. I have n objects and I have to choose at least, at most, exactly k of the objects such that my choice fulfills certain property. This is basically what everything you have, there's always of that shape. But there are many of these problems actually are not of that type. For instance, let's look at one planarity. I want to draw my graph. I mean, one planarity, I want to draw my graph 1 crossing per edge. And I want to parameterize that by 3 depth or something. Well, I need to tell something for everything in my graph. It's not that I have to tell k things, I have to tell something about my entire graph. So it's unlikely that this problem is complete for these classes in the W hierarchy. And the intuition is, if you are in the W hierarchy, you have a certificate where the number of bits is a function of your parameter times log n, because you have k, or k. But for one planarity, your certificate is if you. I cannot imagine how you do this with a certificate with less than n bits. That's also really goes against your intuition. So the question I had at some point, and I looked at another problem, come by that. The question is, for what problem is actually are these classes? Are there classes for which we can say that these problems are actually complete? And if so, does that help us to get even more insight? So that's the question. And then this problem, my story started with a problem called bandwidth. I don't know if you know bandwidth. It's a very old question, because bandwidth actually comes from a Gauss elimination. If I have a symmetric matrix and I want to permute the rows and the columns of the matrix such that all the non-zeros are at a small band along the main diagonal, that's where the name comes from. But in graph terms, would you call this a graph drawing problem? Yes, okay. Good, good, because I wanted really graph drawing examples. But so the question is, I take a linear ordering, a numbering of the vertices from 1 to n, such that for every edge, the difference of the numbers of the endpoints is at most my target value k. And so this is a layout of bandwidth 2. And this is basically that problem. So in 1983, Monin showed that this problem is NP-complete, even for a very special class of graphs. He called it caterpillars, but because I heard that people call what Monin called caterpillars are actually subdivisions of caterpillars. So what I have is I have a path, and I can attach paths of arbitrary length to this main path. So I would call them now long hair caterpillars. And if you have only hairs of length at most 3, then the problem is already NP-complete. In almost at the same time, Gurari and Supero, they showed that the problem is an XP with an order n to the k+1 algorithm. Then in 1994, I was looking at this problem together with Mike Fellows and Mike Hallett, who was at that time a PhD student of Mike Fellows. And we looked at this bandwidth problem, and we wrote a paper, and in this paper, we claimed that bandwidth is WT hard for trees for every t. But in 1994, you could get away with stating a result in a paper without having the paper written in full. That was so we knew it was true, but I didn't have the paper written out yet. I actually promised to Mike that I would write that part, and at the same time, Mike Hallett, he had basically this intuition and thought that, yeah, it's probably not in this W hierarchy. So what happens then afterwards? So 20 years later, Draghi and Loksanov at least showed that this problem, wrote down this proof that W1, that bandwidth is W1 hard for trees, and they gave a lower bound based on the exponential time hypothesis. And sometimes Mike Fellows met me and said, Hans, you promised that you would write this part. So finally, 2020, Corona, I was locked up in the summer at my attic. Nobody was talking to me except my wife. So I've thought, okay, this is the moment, and I finally took the time to really write down this proof and actually sharpen it a little bit and show that it's the WT hard for long hair trees. And then the question came back again from, okay, but hard, but for what problem is it complete? And then we actually, together with so in 21, there was this moment we were actually allowed to stand in front of a whiteboard, and we took this as a question to think about. And we showed that it's complete for a class which I now know will want to call XNLP. So how do you come to XNLP? Um, and the way to do that is to actually look at the XP algorithm. So what is the XP algorithm doing? It's a kind of dynamic programming. And the idea is that if I have an initial sequence, so say I tell you what are the first L elements of my possible solution, what do I need to know of this for dynamic programming? Well, the last k vertices are important because they can have neighbors later. And then I need to know which vertex I already had. But to know what vertex I already had, I need to know only the neighbors of these last k vertices, because I cannot jump over the last k vertices with an edge. So I have this dynamic programming algorithm, and basically every table entry has k vertices and a constant number of extra bits. And this is how the algorithm works. So what you now can do is take this dynamic programming algorithm, but turn this into a non-deterministic algorithm. I mean, if you have at automata theory and you want to know from a regular language, non-deterministic natural language, to go to a deterministic natural language, you build basically a table. And you do the same thing in reverse. So what you do is you have this deterministic algorithm which builds tables, but instead I guess one element in each table. I guess just the next element I use. And so this gives me a non-deterministic algorithm which guesses just one table entry from each of these tables. So what is this algorithm? What are the resources that this algorithm is using? Well, I have k vertices, that's k log n bits. I need to know where I am, which table I am, it's log n bits, and then a little bit more. So I say I have order k log n bits in memory except for my input. And then I use order k n time. And actually, this is an algorithm which fits in a class which was defined in 2015 in a paper by Elberfeld, Stockhausen, and Tantau, and they called this class NF polylog, which are problems which you can solve on a non-deterministic Turing machine in per FPT time and a function of your parameter times log n space. And they showed also a number of problems to be complete for this class. Which most interesting, I think, is a problem on strings, longest common subsequence. This was actually, nobody really looked at this. They actually didn't even mention this result in the abstract of their paper. But this was actually really what we needed. So I found this NF polylog too long, so we decided to call it XNLP because that is really much nicer to pronounce. So where does this fit in the landscape? So people have looked in complexity theory at problems with logarithmic space. I mean, in classic theory, you have L, which are deterministic problems in logarithmic space. NL is non-deterministic, and both of them imply that the problem is polynomial. Now, in parameterized, people have looked at XL, which is deterministic log n space, and XNL is non-deterministic. And here we have two different restrictions, both on the space and on the time. And all of these are subsets of XP. And basically what you then can get is that, with a series of reductions, you can show that lots of problems are actually complete for this class. So I think last year it was shown that ordered level planarity parameterized by the number of levels is XNL complete. So that's an example of a graph drawing problem And we showed in 2021, so that bandwidth is actually complete for this class. So there are other many problems which you parameterized by path width. You can actually show that they are complete for this class. What also is nice is that reconfiguration problems where the number of elements you want to reconfigure are complete. For instance, you have click reconfiguration, you have 2 clicks and you want to change every time one vertex to another vertex, but you need to keep a click of k vertices. And the number of vertices is your parameter. But there are lots of others. Many problems which you parameterize by a linear structure like path width are complete there if you have an XP algorithm. I have 12 minutes left, so I will skip a little bit because I want to go. Yeah, I mean let's really do something which is so many problems on path decompositions with parameter where the path width is your parameter are actually complete for this class. And the membership is often very simple. The membership is namely, I take the existing dynamic programming algorithm. The existing dynamic programming algorithm builds for every bag of your path decomposition, it builds a table. And instead of taking this deterministic algorithm, I just guess from each of these tables the next element. So I get a non-deterministic algorithm, and for these table entries are usually something like order of k log n bits. This is what you typically have per table entry k log n bits. So you have k log n bits for in your memory here. Yeah, no, let's go. Really. So that's XLP, and I mean there are, I think now many problems already shown to be complete for this class. Let's see if I. Oh yeah, I want to tell first this one yet. Completeness for this class actually tells you something, because at least if you believe a certain conjecture. So building upon an earlier conjecture, Michal Filipchuk and Wagner, they came with a conjecture about a problem on strings, but it translates to the following question. Let's say if you have a problem which is hard for the class X and LP, then there is no algorithm which simultaneously uses XP time, so order n to a function of your parameter time, and FPT space, function of a parameter times a polynomial space. So in other words, if your X and LP hard, you want an XP algorithm, you need also a lot of space. And this is also really what you see in practice, because all these algorithms for these problems use dynamic programming and they build large tables. And really in real practice, you also see this, because if you actually implement this algorithm, then in many cases, the space usage is the problem in practice as well. I mean, I had this problem and I run it on my laptop, and then at some point, my laptop says, which doesn't mean that it's angry at me, but because it's swapping information from my hard disk to main memory and back. And then it basically becomes something like 1,000 times as slow as that before. So this is, and of course XNLP hardness actually also shows hardness for all the classes in the W hierarchy, and in many cases it actually gives simpler proofs that you're complete for all the classes. So even people who don't like XNLP, but like the W hierarchy, they can use it because they get simpler proofs. Okay, so then I mean, I had these problems, and many of these problems parameterized by path width are complete for XNLP. But then the question, of course, you know what question I will ask then. What about tree width? What happens if you parameterize by tree width? And the dynamic programming for tree width has a different structure. For path width, you compute one by one by one. By tree width, you have a tree. You compute something in the left, something in the right, you combine it up. So this is probably different. So you can tree width or click width or other of these tree types problems. And then the question is, for what class are these problems complete? And well, we, together with Carla Groenland, Hugo Jacob, and both the brothers of Philipchuk, we looked at this, we looked at some older literature, and then we came up with a class which we called XALP. The A becomes from the fact that one of the definitions has alternating Turing machines in it. And there's actually, it has classic variants which are called. So the idea is where XNLP characterizes path-based dynamic programming, XALP characterizes tree-based dynamic programming. So you have a number of different definitions with how you can use alternating Turing machines or circuits. The simplest of the equivalent definitions is the following, that I have basically almost the same thing as tree width, as XNLP, but I also have a stack. So, so I have a problem and can use a non-deterministic Turing machine which uses FPT time, function of k times n time, and it has two types of memory. Actually, it has three things it can access. It can read the input without changing it. Then it has this part of my memory which I can, the word memory, which I can change, which has, again, fk and log n bits. But it also has a stack. But the stack functions like a stack. I can put something on top of it, and I can put something out of it, but I cannot access something below the top, unless I removed already everything there. So, and the stack intuition here is really, I mean, if you look at the tree, let me go. I mean, if I have a tree, basically what you do is you compute this, you put this on the stack, you compute. Then if you want to combine here, basically, you can. So what you can do is to prove that something is in XALP. Well, you have this dynamic programming algorithm. I do basically, again, I guess for every table entry, I guess the element. But yeah, if I guess the element, I go put these things on the step, go up. I mean, and you want to compute something, remove the top from the stack, and then once you compute it, put it on the stack again. And in this way, you get proofs. And the classic DPs, they are always formed to an XALP membership proof. And for hardness, it's again the same. You have the series of reductions. You start by a Cook-style proof that which shows that some first problem is I use a problem called a kind of generalization of coloring is complete, and then you have reductions. Now, more reductions you have, how easier it gets, because at some point you have in your library of problems, you have something you might use. So there are lots of these problems which are complete. And also problems on planar graphs are complete. Together last year with Cristina Sigliacci, we showed that if you take planar graphs and as parameter you take the outer planarity, that's the number of times you have to remove all the vertices. You have seen the outer planarity this morning. So if you take that as parameter, then lots of problems are actually also complete for planar graphs for this class XALP. So so you have this whole series of reductions. So one of the interesting ones is take this problem upwards planarity with tree width as parameter, which was shown to be W1 hard by Janssen et al. 2 years ago in this conference. Now, you have from Turing machine acceptance, you go to a problem which I call binary CSP. Then you can use crossover gadgets to show, and then actually an embedding of a graph of bounded tree width in the plane which has planarity, outer planarity bounded by tree width squared. And then you get that binary CSP with outer planarity as parameter is complete for XALP. And then we go to another problem which is called all or nothing flow. And I have only 2 minutes, but this is a wonderful proof. It uses Sidon sets, which is the same as Golomb rulers. And what is a Sidon set over a Golomb ruler? It's a set of integers with the property that every pair of integers has a different sum. And you can use that to actually code things and play with things, and then suddenly everything works. I should. But then, if you then read this paper of 2 years ago of the graph drawing conference, they start actually with all or nothing flow. And then you take just their series of reductions, and this is a long and clever proof. Those who were here 2 years ago have seen it. But you can just use then plug that reduction in after that one, and what you get is actually that this problem X upward planarity for tree width parameters actually complete or hard. I didn't look at the membership proof yet, but it's actually hard for this class XALP. I expect it's complete. And then there is this very elegant proof, which I skip. And then there are more problems which are complete for this class. But let me use the last minute to summarize. No, I have still 7 seconds left till it's 3 o'clock. This one. Okay, so I hope I introduced you a little bit to this rich landscape of W hardness, and I hope that you learned something that I think these are useful concepts also for graph drawing problems. The other thing which this talk did was introducing 2 of these new classes, which I am very enthusiastic about because it really captures the complexity of problems which we solve by using dynamic programming, where XNLP looks at if you have large tables which you compute sequentially, and XALP captures if you have large tables you compute in a tree-structured manner. And hardness actually, why I think it's nice, hardness actually tells us something about the resource usage. It tells us that if you are hard for these 2 classes, then if you assume this hypothesis, then the XP algorithms for these problems do need much space. So I think it's interesting if you know that the problem is hard for W1 or W2 to see if you can actually get it to XNLP or XLP completeness. So I hope that that was actually what I wanted to tell. So thank you.
All right. Questions? So did I understand correctly that this proof that upward planarity for tree width is XALP, you just proved this for this talk?
No.
No, it was proved before. Is it published?
No.
It just follows.
The problem is that there is no real proof, right? we proved this. There are two Lego bricks.
Right.
And there's actually no written part where people put the Lego bricks on top of each other.
I see. All right. So this is using this result and your like this one here.
Yeah, I mean if you use this result here, which we had is this paper, and you plug in their result, then you get this for almost free. I think there are 15 lines to show that the connection is right, but yeah.
Right.
But there's so there's after this you don't need to be clever anymore, but just see that there are two Lego bricks which actually fit together.
Okay, thank you. Any other questions? Okay. Oh.
Thank you for the talk. If I were to drop the non-determinism from the XNLP, so I get XLP.
Yeah.
Is there anything interesting in that class? An interesting problem?
Yes. We have. Let's see. There in this reconfiguration question, we have two graphs, a click in one, and we have one graph with two clicks, and I want to move the one click to the other click by every time changing one vertex, and it should stay a click. And you could have the same game with different independent sets or and dominating set, and all of these work. Now the question is, how hard is this? And then there are actually 4 flavors. That is. Anyhow, the number of. You can look at the number of, thank you very much, the number of moves. So if the number of moves, it could be a parameter, and the problem is complete for W1. It could be given in unary, and it's X and LP complete. It's given in binary, and it's complete for X and L, and it's unbounded, and it's given, and it's complete for XL. So it really depends. So and if you look at how these classes work, then I mean I can talk there again 10 minutes about this, but. This one has really also a wonderful proof because it actually follows from the fact that a symmetric Turing machine, something with symmetric Turing machines. Anyway, for in the break if you want to know that. But so this is I think, but this is the only really answer. So I think several of these reconfiguration questions are like that. And the interesting thing is here that you can actually have solutions which need an exponential number of steps. I don't know if you know, some of these puzzles, you have to really, lots of steps, and really more than polynomial number of steps. And that means that you're going to get in the Hartford, get in that class.
We were warned that we are running out of time, so thank you again. So let's thank the speaker again. Thanks a lot.